Good evening, all of you. My name is Anil Yadav, and today it's our 12th tutorial on fundamentals of micro and nano fabrication. Today we will just see whatever we have read till now. So this is the last tutorial today. So I will brief you about the outline of this course. If you have any doubt, you can ask me. So you can stop me in the middle and you can ask me. So in this one, whatever we have read from the beginning, so why do we need the microelectronics and all these things, how this field gets developed, and what kind of substrates, what kind of processes we have done to for the devices, so that we will see. So why microelectronics actually? So as you can see in this world, modern world, you have miniaturization of the things, like from a big room size computer to just a mobile phone that is in your hand, that is possible because of the microelectronics only. Okay, so a very you have the whole world in your hand just because of the miniaturization of these devices. Okay, you can do anything with your mobile, like this is the beauty of the microelectronics. So like a miniaturization doesn't happen, like it costs a lot of things, like you need to there is a whole process from beginning to the end to get the mobile phone. Okay, so there are devices like LEDs, transistors, memories, ICs. Okay, so resistors, capacitors, inductors, so all these things are on a same board. To integrate all these things, it is not an easy task. So and there are other things that you would read in devices course, but this course is mainly for the process of the process. Okay, mainly for the fabrication. So like from there are two things, cost and miniaturization. As you can see on this curve, this is a like 13 micron technology at this point, and now it's around 10 micron, 10 nanometer technology. Okay, from a very large size to a very small size transistor, the cost per transistor is decreasing, and uh, as size is also decreasing, and cost is per transistor is decreasing, but you need a lot of transistors. Okay, you need a lot of transistors. There are billions of transistors in a single chip. Okay, so so that's why the total cost is higher, but the cost per transistor is decreasing. It doesn't cost anything, just a single transistor, but the total cost is higher because 8 GB RAM is there, 8 GB, 16 GB of RAM is there in your mobile phones. Okay, so and another thing is uh, cost is decreasing. That is the one thing. The another thing is the performance with the miniaturization. Okay, with if you are increasing, you are decreasing the the size. Okay, this is your decrement in the size. This side you are decreasing the the size of the transistor. Okay, but the leakage current. Okay, as you are decreasing the size, the leakage current is increasing. Okay, higher the transistor performance, transistor performance, this is the higher the transistor performance, higher the leakage current. Okay, leakage current is higher, but if the transistor, if uh, okay, so because of the gate, if you are miniaturizing the things, you need to play with a lot of parameters, like constant field scaling is, you must have read in the devices. So with if you are decreasing the channel length, then you need to decrease the dielectric thickness, you need to decrease the doping or accordingly you need to manage the other parameters as well. So that is why if you are decreasing the dielectric thickness, then you are also compromising the leakage current. Okay, the maybe the gate leakage current, or if you are just turn off voltage, turn off current, that is the turn off current. Let us see the first this transistor characteristics once. So in transistor characteristics, what you will see is, okay, so in transistor characteristics, what you see is, so let us say for a n-type transistor, this is the in a log plot, this is ID versus VGS. Okay, VGS gate voltage. So in a log plot, if you see, it will be coming like this only. Okay, this is the subthreshold region, and this is the off current, this is the off current, this is the off current. Okay, off current, and this current is, this is the on current, on current. I on divided by I off should be as high as possible. Okay, like 10 raised to power 6, 10 raised to power 7 is desired, 10 raised to power 7. And also this transition is nothing but, this is the subthreshold swing kind of, that is subthreshold slope or subthreshold swing, so that you can say, so how much current is voltage is required to for a decade of change of the current. Okay, to increase the current by a decade. Okay, that is the subthreshold swing. So this is like in millivolts only, and that is desired so that how fast your device can turn on and off fast, or we can say the voltage, minimum voltage should be required, so this low current and this current. Okay, so actually what happens is, if your off current is higher, let us say this voltage, this, so if your off current is higher, you have turned off the device, but still your off current is higher, so there is a power dissipation. Okay, off power dissipation, turn off power dissipation. If you would see, if you are just buying anything like TV, mobile phone, so the battery drains itself. So why does the battery drains itself? Because of this off current only, because there is always, to turn off the transistor, there is at this voltage that the current is there. Okay, that current is the leakage current, and this is because of this current your battery is draining. Okay, when your phone, you are not using your phone itself in turn off condition. Okay, that is the case. So these are the, so if you are decreasing, this is the source and this is the drain, let us say, and this is the channel length L. Okay, if you miniaturization of things in that sense, you, okay, let us see. Okay, okay, hello Ajikit. Okay, hello Ajikit.
Hello, hello, Ahmed.
Hi Ajikit. So do you have any questions, or I'm just revising the things?
Yes, revision would be perfect, Ahmed.
If you have particularly questions till wet etching, so you can ask, and I'm just going through the just transistor characteristics I was going through. So
Okay, okay.
I was just telling about the why the miniaturization of things are giving us a higher leakage current as well. So that's why
Okay,
power dissipation is going high during that. So uh,
okay.
so if you this is the devices on for the device's purpose. So if you have any doubt, we can go through your doubts. That would be much better.
Okay, let's say actually I have no specific doubts as of now.
Okay.
As you explained, whenever I don't understand, I will ask.
Yeah, sure. So,
Okay.
okay, yeah, sure. So, you know about the transistors, but this is not required for your exams actually. So, I was just telling about the transfer characteristics of the transistor.
Okay. No, it is okay. I was also in your course for the fundamentals of semiconductor
Okay.
devices.
Yes.
Ah,
Okay. So if we decrease the channel length, let us say this is the source and this is drain. If you decrease the channel length, so so what will happen is, so this turn off current will be higher. So there will be a power dissipation during the off only, in off state as well. Okay, so if you are so that is why your mobile phone's battery keeps draining while you are not using them. Okay, so
okay.
huh. So the another thing, so how do we make these kind of small features? There are some processes to get the final device. So first is the like a selection of the substrate. So selection of the substrate, most of these things are on the silicon based substrates. Okay, so you can use silicon substrate. You can, for flexible electronics, you can use PET substrates. So that depends on the your applications. So now the foldable kind of mobile phones are coming, and all these things, they use the foldable flexible substrates for that. And the material quality should also be good. So so if you are folding your phones in 4 or 5 times, then it is breaking. So that also not desired. The material and the quality, the mechanical strength should be good enough so that you can use that for a longer time. So then comes the additive processes. After, if you select the substrate, desired substrate, after that you do the deposition of the layers. Like if you are making the transistors only, or then you need this substrate may serve you as a gate, like highly doped n++ substrates can serve as the gate, and then you can deposit desired layers, like for SiO2 you can do Al2O3, you can do hafnium oxide. So these kind of like high K dielectrics are also desired, like HFO2, for better performance of the devices. But there are some other drawbacks as well, like for gate leakage, gate dielectric breakdown, dielectric leakage currents. So these are also there. And then comes the patterning. So if you want to make the devices, then you need to pattern your substrate, so so that you can deposit a source and drain. Or if you are making the LEDs, then you also need to pattern the to get the bottom contact as well. Okay, so there are multiple layers then that you need to deposit. So these two processes, lithography, then additive process, then again lithography, additive process, then these three processes, not the two processes only, these three processes, additive process, lithography, and subtractive process. For if you have 13-14 layers of materials, for you in your mobile phones there are up to 40 layers. So these are done with like deposition, then lithography, subtractive, then again additive process. So many processes, these processes gets repeated over and over again. And also your material that you are depositing, with the processes or with the subsequent processes, that material should also withstand with the subsequent processes. Like if you are making some kind of OLEDs, let us say, most of we are going towards the solution process, so that uh, in silicon technology there are very highly sophisticated instruments are used, like diffusion and ion implantation, oxidation. So these dry oxidation, wet oxidation, these are kind of complicated and takes a lot of energy. These processes are energy intensive, and the machines used in these are highly expensive as well. So most of the technology is going towards the organics because of their solution processability. You can do over a large area. Nowadays solar cells are coming in the market. They are the process to make those solar cells. Okay, the process to make those solar cells is very cheap, very cost effective, because just you just need kind of painting with the paint brush, or you just doctor blading in the sense you just put your solution, coat take the blade over that, so that can coat just the sense is just you can make the solution, you can just paint that solution, that's it. So that can make the devices. So why we are so towards the silicon technology? That is because of there is are other advantages. Not only the mechanical flexibility or other for the organics, but high mobility, high conductivity, and stability. The main issue is the stability. We are still in the silicon technology too much that for at higher frequencies for RF and these applications. So these organic based devices cannot work, okay, because of the mobility and the charge traps and all these things. So these organic devices cannot work. But for solar cells, these are coming in the market. OLEDs, these are coming in the these are already in the market, commercialized. So these are still, there is still gap, okay. So that is the gap is there. That is because of there are a lot of materials, and still this mobility is not up to the mark, okay. So and so that is because of that part is just particularly for the organics. Now let us go to the next one, the selection of the substrates, okay. So uh, most of these now silicon technology we are reading about, because we are doing lithography in this course. This is mainly towards the silicon technology only. So in this one we use the wafers, silicon wafers. These are the substrates, the desired substrates, because of these there is advantage of using the silicon because of very good interface of silicon dioxide interface, and good tunability with the doping. You can tune the conductivity of this material very like you have very good control over because of the over the years. This is highly mature technology, that is why. And extremely pure you can get, because there are some methods like Chakralski method and zone refining method. Through that these wafers are prepared, and in you can get a very good pure silicon, so to reduce the traps, okay. So so that's why and you can get a very good mobility in these. So this that is why silicon is still in the market, still like dominating in the market, okay. Substrates like in silicon is mainly used, and for insulators sapphire is alumina, so that you can use for insulators, okay. In semiconductors, Ajiket, if you have any particular doubt, you can ask me. So I am just going through the semiconductors. Okay.
Yes. I will stop you,
Yeah.
Anil, whenever I don't understand. Thank
Okay.
you.
Yeah. Sure. So and now the semiconductors, high conductivity are the conductors. Okay, the materials that we have are like metals, semiconductors, and insulators. So metals have high conductivity because of the free electrons in them. Low conductivity are the insulators like wood, something, because there are no in between conduction band and the valence band. The band gap is very high. The intermediate conductivity in between these 10 raised to power minus 6 to 10 raised to power minus 2 Siemens. So that Siemens per meter, so that could is the semiconductor. Okay. So so the in semiconductors, what is the like the thing that is attractive is the tunability of the conductivity. You can tune the conductivity in the semiconductors by doping. So that is how the all this is the base for all the devices like PN junction device, diodes, and these FETs, LEDs. So this is the base for all these. Okay, memristors and all. So this is about the semiconductors. And what makes it like this is what I told you already, that the in insulators, the conduction band and the valence band, the band gap is much higher. So even there are no electrons at room temperature in conduction band. Okay, so there is no room for the conductivity for to move the electrons. In the valence band is fully filled, and there is no room, there is no kind of empty states where these electrons can move. Okay, so and if there is the band gap is high, so at room temperature there are not sufficient electrons in the conduction band that can give us the conductivity. But in semiconductors, that is around in between 1 to 3 electron volts. Okay, so in them around if the band gap is less than 3 electron volts, during that or 4 electron volts, that we can say, during in that case at there is a possibility of finding the electrons in the conduction band according to there are some equations in the devices that you must have read. So at room temperature in silicon, around 10 raised to power 10 10 number of electrons you can find in the conduction band. So they can move there because the in conduction band energy levels are empty. Okay, they can move with the application of the electric field. So there is and if you dope this semiconductor with some metal, some other other elements in the periodic table with the third or fifth group, so you will find p type and n type respectively with the doping. So hole dominating and the electron dominating conductivity, dominating the charge carriers. Okay, so so that is for the semiconductors. So you can tune the conductivity with the doping. Okay, that is the thing. And in metals, these conduction band and valency band are overlapping, either overlapping, or we can say another thing is the conduction band is half filled. If the conduction band valency band is half filled, in that case in valency band itself there are empty states and electrons can move. So electrons or holes can move, so that is why you get the high conductivity. Okay, now so doping is of the semiconductors is done by third. Okay, okay, this is fourth one. Okay, there is n-type doping. The fourth group elements you can dope like antimony, this one, phosphorus, antimony, arsenic. You can dope the semiconductors, silicon with this group elements. So then you will find the n-type of the semiconductor. If you dope it with the third group like boron, aluminum, gallium, or indium, so that will be give you a absence of one electron, so you will find a whole yeah, positive type of carriers, that you can say p type of semiconductor.
Yeah.
So
Anil,
yes, yes,
here I have one doubt.
yes, yes.
In the bottom figure, na,
Mhm.
where we have written that antimony and for boron,
Yes.
the level where we specify the Fermi level. Okay.
Which one?
So,
This one.
in both the cases,
Mhm.
let's say in the left image we have shown the Fermi level above the electrons level, right?
Okay. Mhm.
And in the right image we have shown the Fermi level below the whole level.
Okay.
So and Fermi level, as we know, is where probability of finding electron is exactly 50%,
Okay. Yes.
right? So I want to understand like why it is above electron level in the left case,
Mhm.
that is n type,
Mhm.
and in p type it is below whole level. So like I want to
Okay.
understand the SAQ.
Okay. 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 So in this one, what you can say is, okay. So okay, let us take the example of these electrons first. Okay.
Yes.
So in this one, so Fermi level is a hypothetical concept, first thing. So
Right.
this is not a n level like energy level, which are empty or full or something. Okay.
Correct.
And this at this level, but there can be electrons if there are empty states. If not, then you cannot find the electron at this point. Okay. At Fermi level there should be the probability, that is the probability of finding the electron is half, but you are not sure that you can find the electron if there is empty state. But as this case is a pure semiconductor, okay, pure semiconductor in the sense there are uh, no states in between the conduction band and the valency band. Got the point? Pure semiconductor, as in pure semiconductor there are no defects in the sense there are no states in between the conduction band and the valency band. But if we dope the semiconductor, then electrons, there will be states will be created, okay,
Correct.
at this point. Okay. So so okay, and those Fermi level says that all the states above the Fermi level should be empty and below the Fermi level should be filled. That's the got the point.
Okay.
So that is why the electrons are below the Fermi level here.
Okay. Understood. Left side understood.
In the right side, these holes are nothing but the absence of the electrons.
Mm-hmm.
Okay. That
Okay.
is why these are holes. The holes are above the Fermi level.
Mm-hmm.
Okay, the above the Fermi level, all states should be empty. Hole is nothing but the empty state that should be filled.
Correct.
Got the point?
Understood.
Yeah, that is why the holes are above the Fermi level and electrons are below the Fermi level.
Clear. Thank you for the explanation. Yes.
Okay. So now, all these processes are done inside the clean room. So why? Because if you are doing the lithography or you are just doing the diffusion before, let us take from the step by step. First, you need to do the oxide level, oxidation, right? Dry oxidation, let us say. So you need to clean your wafers. During the cleaning, if there are metal contaminants, let us say gold or something, and let us say your sodium contamination in whatever you have, the glass beakers, this is nothing but the soda lime glass. Okay, if you clean your wafers in a soda lime glass beaker, that will contaminate your wafer. Okay, so it is you cannot do the cleaning of the wafer if you are going for subsequent processes like diffusion, or you are making silicon FETs. Okay, you are making any most of these silicon is used for the FETs, because in that only you make the memory stars and all these things. Uh, so so it will kill your device, because sodium diffusion of the sodium is too fast, and it will be all inside your silicon wafer. That will kill your all the devices. Okay, so that is why, the cleanliness, and not only the cleanliness inside, so there mainly the particle contamination is not there inside, because if the dust particle sits, that will contaminate your wafer. And if you are doing, and then comes the lithography after your diffusion or oxidation. Okay, then comes the lithography. In lithography, this is the class 1000 room and class 10,000 room, that 1000 particles per meter cube, that says the thing. And class 100 is 100 particles per metric cube. So that is to maintain the better is the class. To maintain that clean room is highly expensive. So that here that you can see, these are the HEPA filters. These are the HEPA filters. This is HEPA filter. This is HEPA filter. These are the HEPA filters. And as you can see in the bottom of this, there are holes. So there is a continuous flow of the gases, of air, not the gases, continuous flow of the air, that is going through the HEPA filters. The air is cleaned, and there is continuous circulation. And also, to maintain the humidity, there are big dehumidifiers as well, to maintain the humidity. So that because most of the processes are done under controlled environment. Okay, so to do this process, like silicon technology or any kind of gallium nitride or inorganic technologies, so these are highly expensive kind of things. Okay, and you need to be in the gown. The most of the particle contamination comes from your body, so your body should be covered while going inside the clean room, because it is very difficult to maintain the clean room itself. Okay, so and if you are doing the lithography, this is the lithography bed, and this the light is inside lithography is yellow. And in IISc, this lithography section is class 100. Class 100, like you can have only 100 particles per metric cube. So that is because if one particle sits on your device where your device would come, so that will the lithography process will be affected by that. So you won't get the device as desired. So that is why. So there are this whole roof is complete. So here you can see there are no HEPA filters in this region, but in lithography area, you will find everywhere this whole roof is covered with the HEPA filters only. So to run that thing, it is a bit highly costly, and all these things. So now there are additive processes. So depositing the layer, the additive processes are many, like chemical deposition, physical deposition, and these kind of things. So you can do the chemical deposition is CVD, ALD, plasma CVD, and like this. Okay, so and in physical vapor deposition, you just evaporation, you just directly evaporate the material or the substrate, and you can get the deposition. Okay, so we will see that thing. So in this is a just cartoon of the chemical vapor deposition. This is just a process flow. So what things do you need for a chemical vapor deposition is, this is the chamber. This is kind of a chamber that can be a quartz tube, just a quartz tube can be there. So and here you can maintain the pressure at this end of the precursor, and continuous flow of the precursor will be there. So and also one thing is the must is the heating of the substrate, because these reaction take place at very high temperatures. So you can do two things. One is you can heat the whole chamber, and another thing, you can just heat the substrate itself. If you are heating, you can just put a hot plate here, or you can infrared heating you can do with the IR gun, or some, there are some things you can just remotely heat the particular area. So that can be done. So or also you can put a heating coil over just below the substrate, you can do that. So that would protect the this deposition over the walls. Okay. So and but the thing is, to maintain the temperature over a constant temperature over the this wall substrate is a bit difficult, because if you have a 6-inch wafer, so there will be a temperature gradient on of the hot plate as well. So in the middle, that can be let us say 1100 degrees Celsius, but at this end it can be 1000 degrees Celsius. So that would affect the deposition, so uniformity will be compromising in that case. So most of the chemical vapor deposition chambers are heated completely, like chamber itself is heated, so to make the temperature uniformity. So then you will get a uniform deposition over the substrate. Okay. So this is a kind of furnace. Okay, so you just load your substrate in a tray. This is a quartz tray. Okay, this is a, and this quartz, or you can say mostly quartz only, or because metal, you cannot use the metal, that would contaminate your wafers. Okay. And this is furnace with the kind of a quartz tube itself. This is I don't remember what we call it, but this is the base, but that should be non-contaminating. Okay, this base should be non-contaminating, otherwise there is no point. At that should withstand at higher temperatures, let us say 1100 1200 degrees Celsius of the temperature it should withstand. Okay. And so this is kind of a furnace that you can just make in your lab as well. But these gases like silane, these gases are kind of dangerous, so it is not allowed to use these kind of things everywhere. A highly precaution should be taken care while doing these things. Okay. And okay, another thing is, now growth of SiO2. So with chemical vapor deposition, or oxidation, let us say dry oxidation, or these things we do, so we can grow very pristine oxide. Dry oxidation or wet oxidation, the interface at this interface, this is a very pristine in the sense the defects per centimeter square are less, as compared to if you would have deposited Al2O3 or hafnia dioxide, hafnia oxide, or these kind of oxide. If you would grow, certainly they can give you very good dielectric properties, but the defects, they are highly defective. Okay, they are highly defective, that would kill the your devices, because the device performance in that case you would get lesser because of the defects, not because of this dielectric, but because of the interface. This interface, if you are making any FETs, you just need to put a gate over here. Here are the source, and here is the drain. Then at that time you are probing this interface. You are probing this interface as you apply the gate voltage here at this point, gate voltage Vg. So let us say you are applying a positive gate voltage, it would create a negative channel, electrons, it would pull electrons here, so negative channel. So and then you apply a source and a drain, VDS you apply, so there will be a channel and current is flowing at the interface. Okay, current is flowing at the interface. So if it would be this interface would be defective, then the mobility is very low, would be very low. So so that is why a very good interface is required. Okay, so this is the why this another reason silicon, we are kind of lucky that silicon is giving a very good SiO2 interface. SiO2 is dielectric and silicon is a semiconductor, so you can tune the conductivity and you can have very good devices with silicon dioxide. Okay.
Okay.
Yes.
Anil,
Yes.
current flows only through interface or through bulk also? Bulk also current will flow, right?
Bulk also, but okay, let us go a bit more deeper in this case. Okay, so so let us say you have this is your substrate. Okay, so you have SiO2 here, this is SiO2 and this is Si. So if you have an n-type substrate, n-type, okay, so this is I am making a, okay, let us say till here, that is the Si only, Si, and this is your gate. Okay, and your this is your source, this is your drain. Okay, so if you are applying N here, V positive, V is equal to positive, so this is N type already, so there will be accumulation of the electrons at this, that will be accumulation. Okay,
Correct.
so our FETs are not these in our devices, in our mobile phones or these, so these are not used. Okay, this accumulation mode is not used, depletion mode is used. Okay, so when we do the, okay, in this case the current would flow through a hole because there are electrons and it is n type also. Okay, but in case of the other, in if you apply a negative voltage, initially we have applied positive voltage. Okay, now if you
Correct.
apply a
Now.
negative voltage, that will deplete this region. Okay,
Correct.
initially that will deplete and then there will be inversion of the channel. Okay, now there will be holes instead of electrons.
Correct.
Okay, and the holes will be near to the interface.
Okay.
Okay, that will be near to the 1 to 2 nanometer only, 1 to
Okay.
2 nanometer. Okay, the current flows in between through that only, that thickness 1 to 2 nanometer only, as we apply the source drain voltage VDS. Got the point? Otherwise, in accumulation mode, it would be through the bulk as well, but there is no conduction through the bulk, as if we DS is applied, that is there is a depletion region in between this drain and the bulk. Okay, this source and the bulk, there is a depletion region, there is a depletion region. Okay, so through the depletion region there is no current flow, but through the this channel only there will be a current flow. Should I go
Okay.
more deeper, or you understood the point?
I will try to.
Okay, one more thing
reply.
is I didn't tell you is if this is n type. Okay, if this is n type, the source and drain are highly doped p type regions. Okay, source and drain are highly doped p type region. This p type region will make a reverse PN junction with the n type. okay, there won't be any current flow through
Okay.
the N region.
Okay.
Okay,
Okay.
whatever the current will flow, it will be through the channel only.
Okay. Okay.
Okay, that also depends on the inversion layer, for how thick
Mm-hmm.
your inversion layer is. And inversion layer is just a d by length that you can calculate. Okay, d by length, if you took the device course in the
Mm-hmm.
last slide,
Mm.
last lecture, I think, in not in the last lecture, last but one, I think in 11th lecture, you
Yes.
can find the
Yes.
d by length, or you can just
Correct.
search
Correct.
about the d by length, and that
Yes.
is 1 to 2 nanometers only.
Yes. Yes. Yes.
Okay, so the
Yes.
current flows through this 1 to 2 nanometer thick layer only.
Okay.
Okay,
Okay.
yeah.
Hmm.
So got the point?
Okay. Yes.
Huh.
Yes. Thank you. I will go through it again also. Then maybe it will be more clear.
It will be more clear, or
Ah.
I just remember that thing. So if this
Ah.
is N type, then your
Hmm.
source and
Source and
drains
drain
are
P-type है.
highly doped P type, highly
Hmm.
doped, very very highly doped, so that you
Hmm.
can have a very good conduction through them. Okay,
Correct.
these very highly doped will act as conductor. Okay, act as conductor.
Hmm.
This is not
Right.
that much highly doped. N type is not that highly doped. Okay, so
Hmm.
it will form a depletion region, because it would be, it will be also highly doped. Then there the depletion region width will be very less, and there will be tunneling in that case.
Correct. Correct.
Okay,
Correct.
so if you have
Okay. Can you repeat? Can you repeat tunneling वाला zone, please?
okay, so
Tunneling कब होगा?
tunnel, if both are very very highly doped.
Both
And-
means silicon based substrate also is very highly doped.
Yes, yes, yes.
Okay.
In that
So अगर
case.
substrate भी highly doped हुआ तो
हाँ.
वो channel width बहुत कम हो जाता है क्या?
Not channel width, not channel width, the depletion region width.
अच्छा.
Okay,
Depletion
okay.
region width. Hmm.
Okay, I'll show you one thing. Can I just removing this thing? Okay,
Mhm.
just that is just a PN junction.
Mm-hmm.
That is just a PN junction. Okay, if you have this thing, this is N type. Okay,
Hmm.
and you this is highly doped P region,
Hmm.
P plus plus, P plus plus. So if you have seen in so the depletion region, so there will be positive kind of we can say, this was the N type. Now there will be holes when okay, what to say, when you don't apply PN junction, you read, right?
Mm-hmm.
So there will be immobile ions at this junction.
Mm.
Ions, we can say, not we can say, these are ions at this point, and there will be negatively charged ions
Mm-hmm.
because of the at the junction. Okay,
Mm.
that forms
Mm.
the depletion region. Okay,
Ah.
so or we can say, if we say this thing, this is P type, this is the P highly doped P plus plus, and this is N type. So the depletion region width is more towards the lesser doped.
Mm. Correct.
Okay, and if
Correct.
both are highly doped, the depletion region width will decrease. Okay,
Correct.
so
that WANA is equal to WBNB.
yes. Okay,
Ah.
so that
Hmm.
depletion region, decrease in the depletion region, so this width will be very less, so that is why there can be tunneling as well.
Yes. Yes.
Okay,
ठीक है. So दोनों highly doped रहे तो
हाँ,
width बहुत कम हो जाएगा.
Yes.
ऐसा.
yes.
हाँ. ठीक
Okay.
है.
Anything else? You understood that point? 1 nanometer, 2 nanometer is the, because at the interface only the charge.
Yes. Yes.
That current
Yes.
flows.
Yes.
Okay.
Correct. Yes. Clear.
So in okay, the next thing is the one was the chemical vapor deposition, and another one is the physical vapor deposition. In physical vapor
Hmm.
deposition, you already have the material. Okay, the like zinc oxide, silicon dioxide, uh, gold, silver, platinum, whatever. The metals are mostly deposited through the physical vapor deposition, and with the chemical vapor deposition, some oxides or uh, some semiconductor materials like aluminum nitride. Most of the time, these compound semiconductors are deposited through the chemical vapor deposition, and physical vapor deposition, a single element kind of materials are deposited. Most and also people deposit silicon dioxide, hafnia oxide, aluminum oxide. These are also with physical vapor deposition. So you already have the material, and you can do heat the material. You can heat the material that will convert it into the vapors, and these vapors are deposited over the substrate. Okay, so you need to there are some things that you need to have. One is a very good pump. So so the pressure should be very less, like in range of 10 raised to power minus 6 millibar. Okay, this level of pressure should be there. Otherwise, if there are some particles inside, there will be scattering of this material. Okay, so mean free path will be reduced if the pressure is higher. Okay, if the pressure is higher, let us say 10 raised to power minus 3 millibar, so the mean free path will be lesser for the sublimed, or we can say the vapors of this material. So they will deviate from its path, and you will get a very lesser deposition at the substrate. And also, if you have a very less pressure, let us say 10 raised to power minus 9, 10 raised to power minus 10 of millibar, that is also not good for this, because that will also again deviate the path. The deposition, you will get a less deposition in that case, because the pump is running. As soon as you create the pressure, that will be running out through the pump. Okay, so these are the things. So in physical vapor deposition, you just heat this your material directly, like thermal heating. You can just make a coil, wrap it, you can have a crucible, or you can have, so you can thermally, you can heat by passing the current through that. So that can take you at higher temperatures, 1100 to 1200 degrees. So at that temperature, this will get evaporated and taken to the substrate, and you will get the deposition. Okay, so for aluminum, gold, platinum, these kind of metals are mostly deposited with the physical vapor deposition only. And other now new techniques are coming, like inkjet printing for the organics, like materials like PE.PSS, which are conducting and flexible as well. So they can be used for flexible electronics. So just directly you can print the electrodes over that. Okay, and this is the thermal evaporation that as I told you, there is a filament, and in filament you can have some material that will also get heated up to the melting point, and there will be some and then there will be some particles, or we can say it is till the boiling point you can take, and you will get the deposition. Okay, and further, this whatever filament that you are using, that filament should be should have higher boiling point or melting point than whatever you are depositing. So if you that the tungsten, molybdenum, or tantalum, these kind of filaments withstand up to more than 2500 degrees. Okay, so more than that. So, and your gold, platinum, aluminum, they melts at lower temperatures. Okay, so these kind of filaments you can use in that case. And now comes the then patterning via photolithography. Now you have deposited the layer, but you want to make the devices, then you need to pattern the deposited layer. So there are different there are two types of lithographies. Okay, one is direct writing and another one is the indirect writing. So in indirect writing, you just write the pattern over a sacrificial layer. A sacrificial layer like photoresist is used to make the pattern over that, and then you transfer that pattern to that deposited layer and do that thing. So that is the indirect writing. And indirect direct writing, in the sense you directly create the pattern over this. Via a laser you can create, via electron beams you can create. So that is directly you are writing on this without using a sacrificial layer. That is kind of a pixel by pixel writing in this one. So, and in this case, indirect writing, you can transfer the whole pattern in a single go, like with the photolithography you can do that. Okay, lithography is the kind of pattern transfer. So photolithography is the part of lithography, so which uses the photons, or you can say light, to transfer the pattern, to make the pattern also. So the process flow is like you have wafer, you have SiO2, and now you want to transfer the pattern over the SiO2. Okay, over the SiO2. So how you can do that is, first this is the indirect process. This photolithography is the indirect process. First you will coat a photoresist, and then you through a mask or reticle you will shine the light. Okay, so depending on the type of photoresist, whether it is positive or negative, so it will get hardened or will get softer. So after the light illumination, so on the parts where the light is illuminated or where the light is not, so after that we develop this and transfer the pattern over the over this particular photoresist only. Okay, then subsequent processes can be done that will in this region, this photoresist will protect the SiO2. Okay, and this is exposed, this area is exposed, to the outer environment, so you can remove SiO2 easily, like ion beams or something. You can remove this one, etching with chemical. By chemical means like by chemical, wet chemical etching or dry chemical etching, that you can do just to remove this one. And after that you can remove your photoresist, and you will get a pattern like this on the substrate. These are SiO2, and this is Si, this is SiO2, and this is SiO2. Okay, so this is the process flow. So we used a mask over here. What is the mask and how you can prepare the mask is that this is a chrome coated glass. You can have a chrome. This is a, let us say this is a glass that can be a soda lime or quartz. Okay, so and this from the market you can buy. This is completely coated with chromium. Okay, and over the chrome there is a photoresist coated, PR, photoresist coated over the chrome. So that can be positive or negative, depends on the process. Mostly it is positive only. So so over the chrome there is photoresist. So first you transfer the pattern over the photoresist, and then you remove the photoresist from the where the pattern is. Okay, okay, let me show you the whole. This is same this same process. This is the photo. This is just suppose that wafer is glass or glass, and this SiO2 is your chrome, and this is photoresist over that. and you want to transfer the pattern over this mask, okay, over this mask. So finally you will get this kind of, okay, this kind of, but not through the light with the laser. Okay, so in that case you don't require mask, but the laser will write like pen. Okay, when we write the pen pixel by pixel, laser will write over this mask, and we will remove the exposed area first of the PR, and then the chrome under this photoresist is get exposed where we have shine the laser light. Okay, so then we dip this mask, this chrome coated in in chrome etchant. Okay, so you at that time you can remove the chrome. Okay, but this photoresist will protect the unexposed area, and but the exposed area will be removed. So you will get the, finally you can remove the complete photoresist just by dipping it in acetone, and finally you can get this kind of mask. Okay, and this mask is used for the optical lithography, or you can say the photolithography, where you just through this mask you can shine the light, and the whole area can be written within seconds, within minutes you can write the whole area. Okay, but to write this mask it takes hours. Okay, but if you want to do the same process, you want to use the same mask again and again, the same design again and again, just better to prepare one mask and use it for thousands of times. Okay, and how you the tool used to make this mask is the mask writer tool. This is the Heidelberg instruments. This is in Sense department in IISc. So use a laser light. Okay, this is the head of the laser. This I will change the color of the pen. So this is the head of the laser, and over this you can keep this is the stage, and over this stage you can keep your this mask. Okay, you can keep the mask, and this stage moves, and this either that can be anything, either the stage can move or the laser can move. Okay, so that can be done. So this laser, let us say the laser moves with a line. Okay, with the laser moves up and down, and the mask is the raster scanning is done. So pixel by pixel it writes. When as it completes, you can do the development and all these things.
Okay. Anil, just one question.
Yes.
In the previous slide, you
Yes.
mentioned while making the mask, what we do is there is a chrome plate.
Yes.
On that chrome plate, there are certain patterns.
No.
No,
we write the pattern.
we write the pattern by the process you are mentioning now.
Yes, with this we write the pattern. Okay.
Yes, and photoresist is already there, right?
Photoresist is already there over the chrome. Okay, okay, this is the glass. Okay, let me just remove this one. Okay, I'm just showing you the side view, profile. Okay, so this is your glass or quartz. Okay, glass. Okay, this is your chrome. Okay, and over this is the photoresist. First, with this Heidelberg tool, we write the pattern. We write the pattern over the photoresist.
Okay.
Okay, and then let us say you shine the laser light in this region. Okay.
Correct.
You shine with the scanning. Okay, just I am showing this portion only. So, and then you develop it. Okay, you develop it. So what you will get is, this is glass, this is chrome, and this pattern you will get. Okay, after development.
Correct.
Okay, then you do the chrome etching.
Okay.
So in chrome etching, what you will, this is glass, okay, this
Ah,
is your
chrome
chrome,
and yeah.
this is your photoresist,
Right.
okay, after chrome etching. And
Correct.
after this one you just dip in acetone, okay,
Hmm.
acetone. So what you
Hmm.
will get is, you will get, this is chrome, this is chrome, okay, this is glass. My laptop is not working here, there is
Okay. Okay.
problem, okay, this is
But
glass,
understood. Understood.
okay. So you can get this kind of pattern, this kind of pattern. Only
Mm-hmm.
chrome and glass is left in the final stage, and this chrome blocks the UV light,
Okay.
okay.
Abhi is after this step, after acetone,
Mm-hmm.
after acetone, we go to the Heidelberg instrument.
No, 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 no. This initial stage we do the Heidelberg.
Oh, okay.
This
Okay.
is
Okay.
the
Sorry. Sorry.
Heidelberg. The laser that you shine is the Heidelberg. After
Laser.
that, you go to this tool.
Exposure. ठीक है. ठीक है. Clear.
This is the
Sorry.
mask
Sorry.
aligner. Okay.
Okay. Yes. Yes.
Huh.
Sorry. Clear.
So this is the mask. Okay. This is the this picture shows you the projection kind of lithography, but this tool is not the projection kind of lithography. There is condenser lenses, there is light source, this is the light source, okay,
Mhm.
over this, and there are some condenser lenses in this one only, and here in bit at this position you keep the mask, okay.
Hmm.
This is the stage where you keep your substrate, this substrate. This projection lithography is not there in this one. This is a contact or in proximity lithography,
Mm-hmm.
okay. This is not a contactless lithography. Contactless lithography comes with the this projection lenses.
Correct. Correct.
This is the contact lithography. So in this one you can get a feature sizes of up to 2 microns.
Yes.
Okay. So but in projection lithography you can go beyond that, like less
Hmm.
than
Hmm.
1 micron, or you 500 nanometers you can get.
Okay.
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 So this is a, so you keep your substrate over this one, and then you can just move inside, and first you just keep your mask over here, and you can set the
Okay.
parameters in how much distance you want to keep in between your mask and your substrate, so that your mask should not also get contaminated. So if your substrate is sensitive enough, if you just go to the close contact, that your whatever you layer is, that will get damaged. So in that case you can use the contactless, kind of a bit like 2-3 microns of the gap in between them,
Hmm.
okay. So
Okay.
that would protect your mask as well as your substrate, okay.
Okay. Okay.
So then you go for a subtractive process, which is kind of etching, you can say. So that can be wet etching or dry etching. So after patterning, this is the photoresist, okay, and this part is exposed to the outer environment. So this part we can have some biochemical means, this part can be removed, okay. So this is what you wanted finally, and after lithography and dry etching or wet etching, you can get this process done, okay. So wet etching is like in wet etching you do some biochemical means. The chemicals are like HF, or some other chemicals can be there, that can remove the particular layer that you want to remove. So in HF is a well known agent for silicon dioxide, okay. So HF converts this in a soluble product, which is H2SiF6, and H2O as a byproduct, okay. These are the things that, If you want to etch silicon, you first need to convert that silicon in SiO2, and that SiO2 will get removed with the HF. Okay, so there are some kind of these things that are there. So if do you have doubt in this etching?
No,
Okay,
Anil.
these
Etching, it is
okay,
clear.
these etching can be wait a minute, I will just put the charger. This can be isotropic or anisotropic as well. Okay, so isotropic in the sense, huh, isotropic in the sense it will etch in all
In
directions.
all directions.
Anisotropic is directional etching.
Yes,
Okay,
either lateral or vertical.
yeah, lateral or vertical. Yes.
Correct, correct.
Yeah.
Anil, if you don't mind, I will have to drop out of this meeting.
Yeah, sure.
Like, do you mind sharing your contact number? Like, I will not trouble you for anything. Just in case if I need something.
Okay, yeah, sure. So, okay, here I cannot tell. Can you write your contact number in comment box? So I will text you.
Yes, sure, definitely. This is my contact number,
Okay.
Ajiket Patil.
Okay, I will text you, Ajiket. Okay.
Chalega. Thank you, Anil.
Yeah.
We have met, I think, at IISc
Yes,
when I
yes,
was
we
there.
met. Yeah, I remember.
Okay, fine.
Okay.
No problem.
Yeah, thank you for attending.
Yes, thank you, Anil. Yes.
So,
Yes, I will continue for some time. Just in some time, I will have to drop in a few minutes.
yeah, sure. No problem, Ajiket. I think
Okay.
we are done only. There are few things.
Hmm.
I think we are done only. Okay.
Okay.
Yeah, we are done only. No, just etching and dry etching is left. Dry etch is uses the plasma, so to etch the material. That is a kind of gases you can use to etch the material. That is kind of more over the directional etching. Sometimes that you can do. Okay.
Right.
So, I'm also, I think we are done. So finally, after the processing, you can you can have this kind of the whole wafer you can write in single go, and then you can separate out the wafer after dicing. Dicing in the sense you just there are cutting tools like blades are there, so that can precisely cut your dies in small pieces. So whatever you parameter you set, or how this according to the size of the dies, so these dies will be cut, and then you can make the devices out of it. These are the devices only. You can make the final sensors, or after packaging you can make the sensor out of this. Okay, so
Correct.
these
Correct.
can be sensors or FETs or whatever can be there. So you can do that. And
Hmm.
so these are some of the silicon wafer specification. The size that you can have are these are the possible sizes. So as much as 14 inches of the big size of the wafer you can have. So but the thickness of this wafer should be high enough that can it should not break by its own weight. Okay, so if you are picking the wafer from a corner, so it should not get broken. Okay, so the thickness of the wafer should be that thick. Okay, so there are different orientation of the surface, like 110, 100 and 111. So while making the wafer itself according to the surface energy, these are oriented. Okay, the ingot that you get is oriented along the direction. So that is done when you in Chakralski method, how which the seed you put to make the ingot. Okay, there are grades of the wafer. So the like the impurities, according to the impurities, the least impure is the prime wafers. These are the prime wafers which are used for the devices. These are solar grade wafers. There are test grade wafers and mechanical grade wafers. These are for MEMS purpose, micro electromechanical systems with gyroscope or kind of these things. You can have mechanical grade wafers because there is no current is required to pass through them. So, and for microfluidics, for such purposes you can use the test grade or mechanical grade wafers. So there are some methods like float zone, Chakralski or microcrystalline methods. You can make these kind of wafers. Okay, and thickness of these wafers can be as thin as 300 micrometer to 800 micrometer, but can be like 10 micro to 2000 micrometers. Like 2 of thick of wafer should be there to hold for this 14 inches, because if it would be thin, it would break by its own weight if you are taking it from one corner or somewhere, because you can not uh, take it from the middle, right? And the resistivity is can be less than 0.005 ohm to 10 raised to power 5 ohm centimeter. Higher the resistivity, more is the prime wafer. Okay, the prime is the least conductive, because there is the impurities are less in this one. Okay, so to get that prime wafer, these are a bit costly, because float zone method is used to make these kind of wafers. Okay, the finishing is like polishing can be single side polished or double side polished as well. Processing is like oxide coating, that is some after that, after making the wafers, that can be you can coat the oxide or epitaxial coating or these things. That you can do by CVD or dry oxidation kind of things. So from where we are getting the silicon is from the sand to the silicon wafers. Okay, so these are the first polysilicon you feed in the high temperature furnaces, and you make the silicon ingot, and then you do this kind of shaping them to the desired size of the wafers, and slicing them. Then I think this is kind of cutting them in wafers, these ingots, cutting them into the wafers and then polishing them like double side polished or single side polished kind of. So making the ingot from the crystal from Chakralski method is you feed these polysilicon in that in a high temperature furnace, and this is a melt. Okay, this is a melt, then you put a seed and you slowly take that out and you form the ingot in that case, and then it is sliced to get the wafers. If in float zone method, what you do is you heat the zone particularly. Okay, so and move this heating zone to and take the impurities to a one corner. Okay, take the impurities to one corner, so all the impurities will come down to this corner, and here you will get the prime wafers, then you will get a solar cell grade wafers, and then you will get test wafers and mechanical grade wafers. This part is highly kind of impurities. Most of the impurities are in the final part. Okay, and that you can see here as well. So this in float zone refining, most of the impurities are here. So as more number of iterations you will do, like first pass and second pass, third pass, fourth, so this will get more and more purer. Okay, so so that is why more the number of iterations you do, or iterations in the sense more number of passes with the high with that heating coil do, you will get more and more pure at one end and more impure at the other end. Okay, so then you do the shaping in the sense you just polishing it, you make it more cylindrical or to this one, and then just cut the flats to identify the which type of wafer it is. P type 100, then you have one cut on the left side at this, or we can say at the 90 degrees, two flats will be there. If it is N type, the opposite sides you will be having flats. Okay, so this is the thing, and I think that's all for today. So thank you so much for joining the lecture.